Yeah, hi everyone. So today I want to talk about building LLMs, large language models, from the ground up. And this is going to be a coding workshop. So I will show you a few slides, maybe for 5 to 10 minutes, but the remainder of this video will be actually focused on code. I will show you the concrete steps that one might take to implement a large language model from scratch. So just briefly about myself, my name is Sebastian Raschka. I'm currently a staff research engineer at Lightning AI. And we develop an AI platform, and I'm also specifically there involved in LLM research and implementing LLMs. That's currently my focus. And previously I was an assistant professor of statistics at the University of Wisconsin-Madison, where I did deep learning and AI research. So the workshop topics are listed here. So there are 6 topics. The introduction to LLMs, it's this let's say 10 slides I have prepared, but then sections 2 to 6 will be focused on code. So we will be looking at a lot of code examples today. And first I will introduce what the input data to an LLM looks like. And I think this is maybe the most fundamental topic if you want to understand how LLMs work. Because if you understand how the data looks like that goes into an LLM, how it's formatted, and also maybe the data that comes out of it, I think you already have like 80% of the understanding that it takes to, let's say, understand how LLMs work. Then, of course, we will be also coding the LLM architecture itself in section 3. We will keep this relatively brief, but I will show you the fundamental concepts. And then, the exciting part, we will be, pre-training an LLM ourselves on a very, very small data set, because, LLM training takes time. So this is more focused on showing you how it actually works. And then we will train, of course, an LLM, but we will also be loading larger, more capable LLMs from pre-trained weights. So we will also look at that. And lastly, we will be fine-tuning LLMs to follow human instructions. So just for maybe 5 minutes, give you the general introduction to LLMs. If you have not used LLMs, I would say the most common way, of course, would be using ChatGPT. But I believe maybe most of you have done this before. So for example, ChatGPT is an online proprietary service where you can access GPT-4 models, for example. And you can ask it questions or give it tasks. For example, here, fix my spelling errors, and it will hopefully give you a good result here. So fixing, in this case, spelling, but it can also do many, many other things. It can answer general questions, summarizing text, and so forth. So this would be one way of using LLMs via a proprietary service. Another one would be, for example, using your private or custom LLM locally. So you can start, for example, with available LLM, for example, Llama or Phi or Llama by Google. So there are different companies and people and research institutes that share LLMs. And here LitGPT is, for example, a library that loads these different LLMs and lets you fine-tune them. So I'm just showing you one example how I usually do it. So it's a library I help developing. And so here in this case, you can say LitGPT chat, load a checkpoint. And and then you can ask it a similar question or give it a similar task, fix my spelling errors. And usually it performs pretty well because it's a pretty capable model. So this would be the Microsoft Phi 3 model. This would be another way of using an LLM, and a third way would be deploying an LLM API endpoint. So with that, I mean, so the previous example, maybe to go one step back, is about running an LLM locally. In this case, I was using a cloud environment, but you can also do that on your own computer. But not every computer, let's say, has a GPU. And for most LLMs, I would recommend using GPUs, or at least if you want to access more powerful LLMs. If you, for example, watched the Apple keynote recently, they announced to bring local LLMs to iPhones and MacBooks that can run on a CPU, or Microsoft also, I think, has these Copilot PCs where they also focus on running some models on a CPU, but still these are very small models. If you want to really run larger models that are potentially more capable, then it's really highly recommended to use a GPU. And if your computer doesn't have a GPU, what you can do is you can, for example, deploy an LLM on a server, and then you can use it via an API endpoint on your local computer to access it. And it will be kind of like using ChatGPT, but it will be your private LLM. So just to show you an example. So for example, I can do LitGPT serve, and then serving this model. It could be a base model or a fine-tuned model. And it spins it up on the server. And then here in my local terminal, for example, I can then query it via an API endpoint. So here I use an address. So this is like a local address, but you can also specify the port in address. And then you can query it in a Python session, basically. So I could basically deploy an LLM on a GPU server and then use it on a local machine. Or let's say if I am developing a phone app, or iPhone app or something, I can plug that into my app that queries a server and so forth. It's just an example, but these three things, using the proprietary service, running a local LLM, and deploying an LLM API endpoint, I would say are the three most common ways of working with or using LLMs. This workshop is not so much about using LLMs, it's about developing an LLM. So I will, in this workshop, go through several stages. Stage 1, the building, where we have the data preparation and sampling and the architecture coding. Then we will have stage 2 with the pre-training, and stage 3 with a fine-tuning. So this is essentially a whole workflow of starting from data and then ending with an instruction fine-tuned LLM. And in this workshop, because we want to, let's say, keep it relatively, I would say, digestible, so let's say a few hours, 3-4 hours, I won't cover all the topics in great detail, but I will focus on these 4 main points: the data preparation and sampling, coding the architecture, the training loop, and loading the pre-trained weights, where we will be doing these from the ground up, which means really starting from scratch, not using any existing LLM libraries, because I think this is actually a really great way of understanding how an LLM works if we really do all the work ourselves, instead of just, let's say, calling some functions that we don't really understand how they work. So I think this is really important if you really want to understand something, to start from the ground up, or look for resources or code that really walk you through the individual steps that you can then follow and really make sure that this makes sense to you, and then you can also more easily adapt and develop better versions of it, for example. So most of the code for that will be based on my book, Build a Large Language Model from Scratch. So it's currently available on the Manning website. It's a short link here. Or you can also find the code examples corresponding to the book on GitHub. So most of the figures and the code from this in this workshop are from the book, but it's of course not the same as the book. The book is, I would say, way more detailed, where in this workshop we will be covering approximately 20 to 30%. But if you're interested, here you can find more details. For the instruction fine-tuning part, I also have an extensive section on that in the book, which is probably even the longest chapter in the book. However, because I don't want to make this a 12-hour workshop, we will be using for this part a library called LitGPT that I helped developing. So here in this part, the instruction fine-tuning, we will be using also an optimized open source library that is making this very efficient. Okay, so these are the topics we are going to cover. And if you want to learn more about LitGPT, you can find it also on GitHub here. And there is also a cloud environment that you can use. So what I wanted to say is, so for this workshop, there are 2 different ways you can follow along. And I highly recommend, when you're watching this video, to follow along with, let's say, your own code session. So to just, execute it by yourself, also alongside, and see if it all makes sense to you. And you can then also make modifications or change things up and see how it affects the results. And I think that's it's a great way to learn, in my opinion. So there are 2 ways you can follow along. And one is I have a Lightning Studio, which is in a sense like an interactive environment. You can think of it roughly as Google Colab, but it's more sophisticated, where you can run the code examples in the Visual Studio Code environment in notebooks or as Python scripts, and you can also change the CPU and GPU. So for example, for the first part of the workshop, we will be mainly using CPUs, and then because we don't need to use a GPU for that, and then we can flexibly, when we need it, switch to a GPU, but we don't have to set anything up. So here In this one, I have already downloaded all the model checkpoints. I already installed all the dependencies. So it will make your life basically easier. However, if you want to set everything up on your own computer, you can also use this GitHub link here. And there I have all the code examples. But yeah, you have to install the dependencies and download all the files. But it's up to you which, of course, you want to follow. Both have the identical code examples. So yeah, like I said, I would recommend using the Lightning Studio. So in that case, you don't have to worry about dependencies and downloading any files. Alternatively, you can find the setup instructions for all the code here on GitHub under the setup subfolder. And yeah, this is basically it for the introduction. So I would recommend either the Lightning Studio or the GitHub setup to get started. And then I will actually now dive into the code. All right, let's take a look at some code now. So all the code should be here on GitHub under this link. And if you want to use the code locally on, let's say, a laptop computer, I have instructions here for installing everything. But yeah, more conveniently, you can also use this studio. So Open in Studio brings you to this landing page, and then you can duplicate this studio here to run the code like I have it here. And yeah, this contains all the different sections we are going through in this video. And there are also additionally some downloaded model checkpoint files that we will be using later. But so in this first section, let's get started with section 2. We already talked about the introduction, so this was just the slides I showed you. Now we are on to part 2, and this is about the data preparation. So understanding how data input is prepared for an LLM, which is actually quite useful because it helps you also understand what the LLM receives as input and essentially what it has to work with when we pre-train it. This is a Jupyter notebook. I have all the code in here and I will go through it step by step. So it's actually, I would say maybe 20 or 30% of that is taken from my book. Of course, the book is much more detailed, but I don't want to make this a week-long video. So I just, rely on a few smaller subsets, and especially for the figures. In any case, so in this notebook, we will be using PyTorch at the end for data loading and a library called TickToken. But other than that, everything will be relatively from scratch, which means we are not using any other LLM library. And we will get to what that is later in this notebook. So if you run the studio, it should already be installed, so you don't have to worry about it. Otherwise, like I mentioned, if you're running this locally, there is setup folder here where you can find instructions for installing packages and stuff. So getting started with the data preparation and sampling, which would be the first stage when we, let's say, start working with an LLM. That is also, that is true whether we want to use an existing LLM or if we want to even develop our own LLM, because without data, the LLM can't do really much. So in this figure, I'm kind of like summarizing everything that we have to do when we prepare the data. So essentially, we start with input text. That is here just a very small example consisting of 4 words and a punctuation sign, but just, like a simple example that fits into one figure. And the first step would be tokenizing this text, which means breaking this up into individual, in this case, word tokens, and then 1 punctuation token here. And these tokens then get converted into token IDs, which are, you can think of it as number representations of this text. So if this is a text string, these are just integer numbers. And these integer numbers then get converted into embeddings. So I was thinking really hard about whether I should include embeddings or not. And originally, if you see the GitHub commit history, I had the embeddings included, but it ended up being way too much material for this 3 to 4 hour workshop. So I don't cover the embeddings here, but it's essentially a process of converting the token IDs into continuous vector representation. So in this notebook, and specifically in this notebook, we will be talking about this part from input text to the token IDs, and then I will also load the data using a PyTorch data loader. And so the data set we will work with is the verdict by Edith Wharton, that's the correct name. And this is a public domain short story. So public domain means this is a book that has been, or a short story that has been written a long time ago, maybe 100, 200 years ago, something like that. And so there is no copyright on that. So this is like a data set that we can use for LLM training. So if you're preparing data sets, I recommend always being aware and respectful of existing copyrights. So basically saying that we can't just, copy certain texts from the web, because there may be copyrights on it that we then also should be respectful of. In any case, this is a public domain book that we can use, and I'm just using a very, very small book for illustration purposes, so that the training later in section 4 will be relatively, let's say, fast, so that we don't have to wait a week for our model to finish the pre-training. So this text consists of 20,000 characters, and it's just regular text, plain text. So here is an excerpt of the first 100 characters, essentially. And like I've shown you earlier in the figure, the goal here is first to tokenize the text, which means breaking it down into individual tokens, which are words, punctuation signs, and so forth. And it's actually a big topic itself. It could be a whole 4-hour lecture discussing how tokenizers work, but tokenizers are not really the LLM itself. So in this case, I will only show you a simple tokenizer, and then show you a tokenizer that is used for GPT models. But just to get an idea of how it works, here's a simple tokenization scheme. So here I'm using a regular expression that splits text based on white space characters and punctuation and so forth. So everything will be kind of split like you can see here. If you are not familiar with regular expressions, even that is probably a 2-hour topic by itself, or even longer. So I usually also, I'm really not that good at regular expressions anymore, thanks to LLMs, because you can actually also ask LLMs to help you with generating certain regular expressions. The idea here, though, is that we are splitting the text into these tokens. So actually I don't need this line, even it's redundant. So I'm splitting the text into tokens here, and you can see it's essentially one word per token, and then we also have the white spaces here as separate tokens. So these are the first 38 tokens here. If I then print the length, so we have 9,000 tokens. So that's the total number of tokens in the verdict data set. We can also take a look at the unique tokens. So for example, I can do the length and then the set. So in Python, the set gets rid of duplicates. It's basically just unique entries. So I can do length preprocessed here, and this should give me the number of unique tokens. So we have 1,133 unique tokens in this data set. Next, actually I can also show you this if you're interested. Preprocessed. So these are basically the unique tokens. These should be the unique tokens, of course. So these are not containing the white spaces anymore. They are just the unique tokens. I can also maybe sort them alphabetically. Let's see. So here we have the unique tokens in increasing order. In Python, usually capitalized words go before the lowercase words. Okay, so next we can convert these tokens into the token IDs. But for that, before we can do that, there's one more step, and that is building a so-called vocabulary. So looking at this figure, we, let's say, have a training data set. This would be the verdict that we just looked at. The first step that we already did is we tokenized this data set, which means we took this and converted this into these individual word tokens. Now the next step is to build this vocabulary from all the tokens in the training set. So for that what we do is we take or consider each unique token and add it to the vocabulary in alphabetic order, which is kind of like what I've done here. So here I extracted all the unique tokens, and next, once we have these unique tokens, we assign a unique token ID to them. So here they are in alphabetic order, and then I'm assigning a token ID, essentially, just an integer number. You can think of it just like a unique mapping from word to integer. So how I do this is, so here's actually the same code I used earlier above. So to get the unique tokens, I'm calculating the vocabulary size, which is equal to the unique tokens, the number of unique tokens. And here now I create this dictionary. So I say for each, so let's do this maybe step by step. So for each word, for each word I have a for loop for I in enumerate. So this will be giving me IDs from 0 to 1. So I can do print I, and you will see it will go from 0 to 1132. And it will give me also the corresponding token. So because enumerate gives me the number, the index, along with all the unique tokens. So what I'm doing now is I'm using the token and map it to the integer. So I'm basically reverting this. Instead of from integer to token, I have token to integer. So I can actually take a look at this. Actually, I have it already here, so I don't need to retype it. So I can actually look at the, let's say, first 50 entries and can show you then how this looks like. So here we have now the tokens mapping to these IDs, and you can see the punctuation characters come first, and then we have them in alphabetical order. So each, kind of like here, each unique token maps to a unique token ID. In this case, we have 1133 token IDs. And yeah, and then once we have this vocabulary, we store this vocabulary because we need to use it now to convert our text. So we have some sample text here. We tokenize it, which is what we have already done. And then we use this vocabulary that we have just built to convert it into token IDs. So now we are using this tokenized text and convert it to token IDs using this vocabulary. And yeah, you might wonder, where do these numbers come from? That is because how our vocabulary is constructed. So maybe, let's see, it would be down here, but the would be corresponding to token ID 7. So if I scroll up a bit here, so this would be the last entry. It would correspond to ID 7. And then in our vocabulary, brown corresponds to 0. Dog corresponds to 1. And this is how we come up with 701 by just looking up the respective token IDs for these words. We could put everything together into a Python class, and this will make it easier to use this in practice, this concept. So here I have a simple tokenizer class, and before I show you maybe the code, or before I discuss the code, let's take a brief look at the figure here. And so what this tokenizer class is supposed to do is it's supposed to encode text, like here. So you have text, and then you encode it, and the encoding will essentially break down the text into tokens. You can then use the vocabulary to convert these tokens into token IDs. And then there's also a reverse function. It's this tokenizer decode method. And this method will take token IDs. So when we have token IDs here, convert it back into these token strings, and then assemble the token strings back into text. So you go from basically text to token IDs, and then back from token IDs to text. So I can maybe just show you how this works here. So if I initialize a tokenizer, simple tokenizer version 1, I give it the vocabulary, let's say vocab, right? may have to execute. I did execute this. Okay, it should be fine. I need to execute this first, of course. So now when we initialize this tokenizer with this init method, it will store the vocabulary string to integer. So this is the vocabulary we use to map from string to integer that we already created. And then we can also have a reverse vocabulary. So this maps from integer to string. So here it's essentially just reversing it. So instead of string integer, we have integer string. So just to show you how it looks like, let's go maybe here. So I have my vocab that maps from string to integer, and I can say integer string for string integer in vocab. Oops. Keep hitting this down button for some reason. And this should be items, I think, because otherwise I will iterate over the keys. This should work. Yep. So this is now essentially the reverse mapping from integers to the strings. Okay, and so this happens when we initialize it. So it constructs this, and then we can use the encode method. The encode method that can then convert our text into token IDs. So let me from the top grab some. I can actually also go here. Let's just scroll down here. Sorry for scrolling so much. So I can go here to the verdict. Let's just copy some text here and tokenize this text. So here I'm going to tokenize it, and yeah, you see we have these integers now, and I can do the same thing in reverse. So I can take this and say tokenizer decode, and this will be just doing the same thing but the other way around. So we go now from the token IDs to this text here, and yeah, this is essentially how the tokenizer works. So we have a method encode that goes from text to token IDs, and then we have the other way. We go from token IDs back into text. Okay, yeah, this is our simple tokenizer. I already showed you this, so nothing new here. And now I should say, I mean, there's a reason why I called it simple tokenizer version 1. This is really just a very naive, simple tokenizer. It's to illustrate the two concepts of encode and decode. Now in practice, when you use a LLM or a tokenizer, you usually, when you use an existing LLM, you use a pre-trained tokenizer. So when you are creating a new LLM, there's actually a training for the tokenizer where you are applying the tokenizer to a data set, to the training data set, and then it learns a vocabulary, like similar to what we have done before. Now, in practice, there are more sophisticated algorithms for that, and one of them is called byte pair encoding. And what's special about byte pair encoding is that it can handle unknown words. So in this workshop, because this would be another 4 hours implementing byte pair encoding and training it from scratch, we are going to use the tick token library, which is an open source library from OpenAI that is very popular and is used to tokenize text for GPT type models. It's pretty fast, so it's a Python library, but it is implemented in Rust under the hood. And I compared it to some other implementations, for example, the original byte pair encoder by OpenAI that was used for GPT-2, and it was 3 times faster than that. And I compared it also to the BPE tokenizer in Hugging Face, and tick token was 6 times faster. So it's much faster than, let's say, the Hugging Face tokenizer. So that's why we are going to use this particular tokenizer. It's a nice fast tokenizer, and I will show you in a moment how it works. So first we are going to use the GPT-2 version of that, and then really the way it works is very similar to the way we used it before. Also, we used our own simple version 1 tokenizer. So there's also an encode method and a decode method. And it's essentially the same input. So it takes text, encodes it into integers, and then it takes integers and decodes it back into text. Just to show it to you here. And one thing maybe I should mention is this part. And so there is another a specific token called end of text token. And this is a token used by GPT models to denote when a text ends and when a new text starts. So for example, when you are preparing a training data set, you may have multiple books. Usually, for example, when people trained the Llama 3 model, they used 15 trillion tokens, like many websites and books and so forth. And so usually you would insert this end of text token if you train a GPT-like model after each document or each book or website or so forth. So this is really just a text delimiter. And here I'm just showing you that in this particular case for tick token, it's not included for some reason in the standard GPT-2 encoding vocabulary. For some reason you have to explicitly add it here. And this will be then corresponding to the 50,257th token, because in PyTorch or in Python we start with 0 indexing, so we have 50,257 tokens in this BPE tokenizer. One thing that is special also about BPE compared to our own tokenizer is that it can handle unknown words. So what I mean is I could technically go here and say tokenizer encode and then some really made up text, and it will still work. So here in this case, it will still work. I can, for example, say tokenizer to find out what these IDs correspond to. Let's say decode, and let's take the first one is 292. So I'm just taking this token here, and let's see what this decodes to. So it's actually considering this as a token, the AS. And for the second one, it's considering DK. So how it works is essentially that each character can be a single token if it's like this, where it's like an unknown word. But if the model has seen words before that look similar, for example, S or DK, then it will use 2 character tokens. So in other words, what I'm trying to say is it can handle unknown words by breaking them down into individual subparts. There's actually a quite interesting algorithm behind this. I'm not covering it here because it would be a long lecture, but it might be an interesting future video sometime. But we are going to use this BPE tokenizer for all the remaining sections in this workshop. So one more thing I wanted to briefly cover is the data loading. Because I don't want to spend like 5 hours of your time on preparing the data set. I will not go into too much detail of how the data loading is implemented here in this particular workshop. But one thing I think we should talk about is how the data is roughly structured. And so LLMs, when they are pre-trained, they learn to predict one word at a time. So if I have some input text here in blue, it would generate the next word here in red, the learn. So LLMs learn. And then for the next input, LLMs learn, it would generate 2, the next word. And this is usually how we talk about, let's say, the LLM pre-training, the next word prediction task, and so forth. But what really happens under the hood is the LLM predicts the plus 1th token at each position. So it's maybe more clear if I show you this figure here. So here I have some input text, and in blue, this would be my input. I'm not showing you the LLM would see the token IDs, which are then embedded, but I'm showing you the text here because it's a bit more readable. So here, let's say we have input text instead of token IDs, so because then you can better visualize it. So the first input, if I have a context size of 4, would be in the heart of, and then the targets, the thing that I want to predict is the inputs shifted by 1 position to the right. So you can see in blue, it's the input, and in red, that's the targets shifted by one position to the right. So LLMs are really trained, let's say, on target tokens that are shifted by one position. So if I feed the LLM this input, it should generate this output. And how I get this next word at a time here that I'm showing you here is by taking only the last token. So for example, if I have this input, the model generates this output, I would only consider this last token here the basically. So in this case, in the heart of the, so we have one more token, and then the next input would be everything shifted again by one block. So in pre-training, we could move over this blue one here, like I'm showing you here, by one position, and then we can have the next input batch like this. So we have in the heart, and the next input would be in the heart of the, in the heart of, and then the heart of the, and then heart of the city stood, and so forth. So we can always move over by one position, but then you notice that we get these overlaps, right? So we have the heart of here, and we have it here too. So in this case, the LLM would essentially see a lot of repeated tokens when you're pre-training it. So in practice, when we prepare the inputs, what we do is we shift this input window by the size of the input window. So this is also called a stride. Sometimes, if you have worked with with CNNs, convolutional networks, you may be familiar with the strides when we talk about the convolutional kernels. Here it's a relatively similar context or concept. So here, if we have an input of size 4, for one training example, we would then move it over by 4 for the next one, so that we don't have an overlap for the inputs. The targets, I'm not showing you the targets here because it would be too cluttered, but the targets are still shifted always by +1, because you always want to predict the next word. There are actually some LLMs, there's one, actually it's only one, it's called multi-token prediction something. So there was a paper recently by, I think it was Meta AI, who developed a method to predict 4 tokens. But this is really like an experimental research paper. In practice, if you look at all the popular LLMs, for example, ChatGPT, GPT-4, Llama 3, Phi 3, Gemma, and so forth, and Gemini, they all do next word prediction. So it's a sense like the targets are shifted by a position of 1. And we will actually also see sampling function later once we pre-train the network. So then it will be also a bit more clear how you get that next token in case this was confusing. The last thing is I wanted to briefly show you just how the data set looks like. I originally planned to go over this, but this ended up being too much material because I think we are already talking for half an hour just about this section, and there is also still the architecture and the pre-training, weight loading, and fine-tuning to talk about. So I'm cutting it short here, and I will just mention there is this function I implemented, which will then essentially produce the input batches for the model. So here in this case, these are the inputs, and these are the targets. So the inputs are, so the token IDs here, I mentioned I'm showing you the words instead of token IDs because it's more readable. Got the same concept here. So you have an input, and then the target shifted by one position. So you can see the 367 here, and it's located right here, and then 285, 2885, and so forth. So everything is shifted by one position, and you can also see that there's no overlap between any of those. So in case you are wondering about that, it's basically this moving over by one position. By the size, by 4 positions. And here we are using this max length of 4. So we have only 4 per row. So one row is one training example, and we have only 4 tokens per row, which is kind of small. And this is really just so that I could make a figure where I can visualize that. In practice, when we are training a model like GPT-2, it's usually something around 1024. So you have like 1,000 tokens in one row instead of just 4. It's really just so that it's easier to visualize, right? Yeah, okay. And so this is how the input data would look like. So we have mini batches similar to deep learning, where in this case we have 1, 2, 3, 4, 5, 6, 7, 8, a batch size of 8, and each training example consists of multiple tokens, and then the targets are really the same as the inputs except shifted by one position. And so this is in a nutshell how we prepare a data set for an LLM, and we will later train our LLM on this data set. And just like as a warm-up optional exercise, maybe pause this video at this point and prepare your own data set. So if you have some favorite texts, maybe something you have written, or maybe some other public domain book you like, please feel free to download it and put it into the folder where you have this notebook, and then just run this code instead of the verdict here at the top. Run this code on your own favorite text, and then you can actually also use this text in the later sections basically. So it's just like a small, maybe fun optional thing to do. Okay, so now after we covered the input part, how we tokenize texts, let's go to the next part, the LLM architecture. So here in this notebook, I want to talk about a bit of how an LLM is structured, but this is only on a big picture level. So there will be a lot of individual components, and this is a 3 to 4 hour workshop and not like a 30 to 40 hour workshop. So in this case, we will be focusing on the big pictures here. So here in this notebook, we will be talking about coding the LLM architecture, but the top-down view. If you're interested in further details, you can check out my GitHub repository here corresponding to my book, where I have more notes and on every, let's say, individual component that we code. But for this video, let's focus on the bigger picture. So suppose we have a LLM like shown here. Previously, we talked about taking input text and then tokenizing this input text into these individual token IDs, and inside the LLM they get then processed by so-called embedding layers that produce continuous valued vectors, and those go into so-called transformer blocks, and then there is an output layer, some post-processing steps, and then we get text back. So the goal again is to generate one word at a time with the LLM, and that's how LLMs are also pre-trained. So when you use something like ChatGPT, of course it's more sophisticated, so you will notice it can follow instructions, but typically when we start developing an LLM and pre-train it, it will require you to provide something like a starting text, a starting context. For example, like this, every effort moves you. And then based on the starting context, it will provide basically the next word, in this case, forward. There are a few more nuances to that, how this next word is generated. And we will get to that by the end of this notebook. So here it's more like the big picture. We have the LLM, and inside there's something called a transformer block that gets repeated a number of times. And that produces basically the output text. And this is the same for all kinds of architectures. It's GPT, Google's Gamma or Gemma, Microsoft's Phi, Mistral, Meta AI's Llama, and so forth. So they all kind of rely on the same underlying concept. And here's the architecture in a little bit more detail. And I know there is a lot of technical jargon on this one, which we won't go over here. But, if you are familiar with deep learning, some of these things might be familiar to you. For example, dropout or layer norm, or these are residual connections. There's an output layer, feed forward, which is basically a mini-layer, multi-layer perceptron. And this consists of linear layers with non-linear activations and so forth. So again, this workshop is not the workshop to go into these details. I wish I could, but due to time reasons, I have to only give you the big picture overview. And the takeaway here is, I would say, that different LLMs are very similar to each other. Even though they might be large and much larger than others, they are still underlying the same concepts. So here on the left-hand side, GPT small is a 124 million parameter LLM. Of course, the L in LLM stands for large, so it's small, large language model. But there also is this variant called GPT-2 large, which is 1.5 billion approximately. And so this is about more than 10 times larger. But the only difference really is that this number of times the transformer block is repeated is now 36 instead of 12. And we have 20 heads instead of 12 heads in this masked multi-head attention module. So if you are familiar with convolutional networks, in convolutional networks, there is something called channels, and the heads is essentially analogous to those channels. And there's also a detail where they use rotary embeddings. Sorry, not here, that's actually Llama. So here we use absolute embeddings and they have a different embedding size. So when we have the token IDs, we go from token IDs to continuous valued vectors. And in this case, each token ID is represented by a 768 dimensional vector. In the large model, we have 1280 dimensions. So it's just making the embedding size larger. So each vector representing one token is essentially larger. So here I have for comparison also a different architecture, Llama 2, but even that one is very, very similar to GPT. So here in this case, what they've done is they swapped layer norm with RMS norm, and they removed dropout. So dropout is not very popular anymore in large language models, so most architectures don't use it anymore. And yeah, other than that, they use the rotary embeddings, positional embeddings. So it's just a different form of embedding the words. It's just like a cosine, sine kind of wave form to rotate the embeddings to create some notion of position. But again, this would be a great topic for a different video, maybe hopefully in the future. Another detail is they swapped the activation functions. So instead of gelu, they use silu or silu. So they're just, honestly, I would say minor implementation details, but fundamentally they use the same architecture really. So suppose we are interested now in working with this 124 million model. Here is just some, hyperparameter configuration to get this architecture I'm showing you here. So we don't need to really go over those, but n layers is the number of times the transformer blocks get repeated. I could also have called that n transformer blocks maybe. The number of heads here, embedding dimensions. So here, this would be corresponding to these, right? And the context length is how many tokens you can provide as input. So newer LLMs, they support, let's say, up to 4,000, 8,000, sometimes even more tokens, but it makes it also more memory intensive. So 1024 is actually quite a good number for experimentation. And the vocabulary size, how many unique words are in the vocabulary. And this corresponds in our case to the BPE tokenizer, which we implemented in the, or not implemented, but loaded in the previous notebook. So when we loaded that somewhere here, we used the BPE tokenizer, which can represent 50,257 words or tokens. Yeah, we disable dropout. It's not really needed. So honestly, it just makes the architecture more complicated, but we can also enable it, so it doesn't really matter. And QKV bias, it's implementation detail I did here because maybe I shouldn't discuss it. It's too much detail here, but the masked multi-head attention layer uses linear layers. And it's usually common to have a bias unit for the linear layers, but modern architectures don't use that anymore. So in modern architectures, the linear layer is essentially just a simple matrix multiplication, especially when it comes to the QKV matrices in an architecture. So it's basically, instead of applying this affine transformation, we have a linear transformation, a linear matrix multiplication. However, the original researchers who implemented GPT, so the original GPT model, they did use a bias unit for the QKV matrices, which is a bit weird, but it's maybe just what they did. But then if we want to load these weights later, we have to match that. So in this case, I have a toggle, so I can add these, so we can later, we can later load the pre-trained weights. Now, this is just a big picture overview, of course, but there's one more thing I wanted to talk about, and that is how the input output looks like. So if we have the input text here, it gets tokenized as we've talked about in the previous notebook, and then it goes through the embedding layers. We have the transformer blocks and so forth, the layer norm, and then an output layer. And the output actually, unless we do some post-processing, the output of this output layer, because it's just like a matrix multiplication, a linear layer, how it looks like is we get a big tensor here. So we have 4 words, 1, 2, 3, 4 tokens in this case. So we have 4 rows, 1, 2, 3, 4. But each of the columns here, so we have actually 50,257 columns. And the columns here, they correspond to the vocabulary. So it's a bit abstract here. I couldn't, of course, show all the 50,000 dimensions, but we are looking here for the highest value. So if the highest value in this whole thing, in the whole row, is the first value here, then this would be corresponding to token ID 0. The second position would correspond to token ID 1. So if I go back a bit, the previous notebook, we had the vocabulary at some point here. So first token ID would correspond to the first entry, the second token ID to the second entry, and so forth. And in the same way, each column corresponds to the token ID. So the first token ID, second, and then the last token ID in the 50,257 dimensional vocabulary. So this is really how you would implement the LLM. And I'm not showing you the implementation details because this would be a 10-hour lecture, but I have them here in the supplementary file. And if you want to, it's also described in my book and in the GitHub repository corresponding to my book. So if you want to find more information, I have more notes there. So here we are more focused on the big picture. So let's actually create some simple data set. So I have just initialized the GPT model. And here I'm getting my BPE tokenizer that we talked about in the previous notebook. And I have some 2 text inputs. Every effort moves you and every day holds A. And I want my LLM to complete these texts, essentially. So I'm creating a mini batch. So I'm not using the data loader from the previous section, just to keep it simple. I have a very simple input. So the first training example are these 4 tokens, and the second training example are those 4 tokens. So this corresponds to text 1, and this corresponds to text 2 here. And let's put this into the LLM and see what the results are. So you can see the output shape is now 2 times 4 times 50,257. So this is a shape and this is a corresponding tensor. So what do these numbers mean? So we have 2 input examples, right? So we have 1, 2, and this is why we have this 2 here. And then each input example has 4 tokens. So we have 1, 2, 3, 4. That's why we have the 4 tokens here. But each of these tokens is now represented by a 50,257 dimensional vector. So here, that's where this number comes from. So if I take one of those, so if I, let's say, take the first training example and then take the first token, this should give me a 50,257 dimensional vector. So this would be the embedded token. So 50,257 dimensions. This would be the vector corresponding to the first token, in this case, this one. And it's not necessarily just this one, because inside a GPT model, there's this multi-head masked attention mechanism, which also, which implements, sorry, I almost tipped my glass here, which implements like a concept that combines information from all the tokens. But roughly you can think of it as the token corresponding to the first one here. Okay, so how does it now result in the next word that we want to predict? Because now we have essentially as the output 4 tokens. So for each training examples, we have 4 tokens that are 50,257 dimensional, which is like, wow, where does this large number come from, and why does it help us in generating the next word? Because like I told you before, LLMs are all about generating the next word. So how do we get from this multi-dimensional concept to just a token, a text token? So how do we get from this to this? And yeah, how it works is a bit complicated, but I think if we go through it step by step, it should hopefully be a bit demystified. So again, taking it from the left-hand side slowly, in the last notebook, when we had some input text, hello, I am a, let's say this is my input text. What we did is we tokenized it. So this is now token IDs. And then this goes into the model. And then we get these 4 rows with 50,257 dimensions each. So this is what we just had above. Now, we are only interested in the next word. We are not really interested in all the 4 output tokens. Because like we talked about before, if I go back a bit, where was it? 1 second. Here. So what I showed you before is when we train or create an LLM, it predicts the tokens shifted by 1. If in blue, this is my input, the targets are shifted by 1, right? So in this case, if I have this input, the only new token will be the next one here, the last one, because these, the hard off, they're already contained in the input here, the hard off. So we are interested in the output and then only in the last token of the output. So this means we are only interested in the last row in this case. If I have 4 rows corresponding to my 4 tokens, I'm only interested in my last row here, which corresponds to the new token. Now I mentioned each row will be 50,257 dimensional, and these are the so-called logits. These are just unnormalized scores. Typically it's not necessary for generation, but during training we normalize them to obtain probabilities, and these sum up to 1. And what I do then with these probabilities is I look for the largest probability in this probability tensor. So again, I go from token IDs to token embeddings, and then based on the output for the token embeddings, the last token, I look for the largest value. In this case, let's say it's this value here. And this value corresponds to position, let's say 257. I dotted out a few because otherwise it would be too long. And so what I'm doing here is I'm looking for the largest value in the last token, and then I get a token ID, and then I can use my tokenizer decode to decode this token ID back into a word or token string. So in this case, hello, I am is my input, and then I get this A, which is the next token, and I add this back to my input, and then I do another round where now the model gets the original tokens plus a new token, and then again it generates the next one, and so forth. So this is how we get the LLM to generate always the next word. This is how we get this text, essentially, that we start with this one, the blue one, we generate this A, and this A gets added as input again, and then the next word is, let's say, model, and we add this model here back here, take this whole thing as input, generate the next one, and so forth until we have the full text. So it's really just generating one word at a time that we keep appending back as the input. This is sometimes also called as teacher forcing, but I don't like this term. So it's basically just adding the token back as the input. And here's a simple function without bells and whistles to implement this concept. So we iterate over the number of tokens we want to generate. So let's call this max new tokens. And then we get the indices. So here I'm truncating them a bit because, like I mentioned, LLMs can only support up to a certain context size, let's say 1024. In case I have more text than my LLM supports, I would truncate this. But this is actually, for our simple case, not necessary because we have a very small context. Okay, so what I do then is I create these logits. The logits are these values here. Just called logits, and I get the last value here. The -1 is the last position. So the columns are the 50,000 dimensions, and here The dimensions, the rows are 1, 2, 3, 4. I'm getting the last one, -1 in indexing in NumPy and PyTorch is the last one. I apply my softmax function, which gives me these probabilities here. And then I look for the largest probability. Specifically, I look for the position where the largest probability is. So in this case, let's say this is position 257. And this will become then my new generated token ID. And then, yeah, I concatenate the original here, the original indices, with this, next token essentially. And and this is essentially how we generate one word or one token at a time. So here's the whole concept visualized again. We have some input, generate the next token, append it back, generate the next token, append it back, generate the next token, and append it back. And this is how it works, how an LLM generates one token at a time. And so for the exercise, I have not shown you how to use this function. It shouldn't be too complicated, I hope. I have some instructions. I would say maybe pause the video and try it yourself. See if you can use the previous function that I showed you to generate some text. So maybe pause the video here and I will then continue. So for me, it's been some time since I made this notebook, but let's see if I can do this off the top of my head. So the question is essentially how we use this function that we implemented. So let's do some text, some example text, and then we first encode it. So we get the token IDs. So we have the encoded text, let's call it like this, and then we have the tokenizer, encode text. Should work. So we have 3 tokens in this case. And I mentioned here, so we need first to apply the torch tensor to convert this into a tensor. Can do it right here. So this is now a torch tensor. One thing is our network expects a batch size. So the way we coded it is it wants a batch size. We can see that here that, where was it? Here we have 2 batches. So we have to add this batch dimension. In PyTorch, one way to do it is using the unsqueeze. Oops. Yes, sorry. We use the unsqueeze, which adds a new dimension at the 0 position. So let's see how I can show it to you. So if I have just a one-dimensional tensors with 3 elements, I can actually also use, I think, endim. So I have 1 dimension. I can then do encoded text and then do unsqueeze and first dimension. So this should be now adding this new dimension. So now I have a 2-dimensional tensor like this. And we have to maybe assign it to a variable. Let's call this batch input. And then we can use our text generation function. So let's use that. Just copying it here. So we can, I think I just called it model. The indices are the batch inputs. Let's say we want to generate 10 new tokens and the context size, our model has a context size of 1024. Let's see what happens. Not defined. Okay. Let's try this again. Batch input is not defined. Did I not execute this? Okay. Integer object is not subscriptable. Where did I make the mistake here? Oh, I see. I have the endim here. So it should not have happened. So let's just print it out to make sure it looks okay. The 3 tokens with a batch dimension. So this should work now. Yep, so I have my generated output. Now this doesn't really tell me anything because this is very abstract. So let's convert this back into token IDs. So we would use tokenizer decode and then give it our token IDs. I think this will probably, this will give you an error, because I think what we need is we need to unsqueeze. So it's a bit tedious, but we have to, we have to squeeze it now. So this would be removing the batch dimension, and we can actually also turn this into a list. Not like this. I think maybe like this. No. Oh, item is a scalar. I think this should work. It's just like a tensor. Let's try it out. Let's do. Yeah, so we have basically now the text generated here, and you can see this doesn't make any sense. So we can recognize, okay, these are the first 3 tokens we gave as input. That makes sense, right? Some sample text, but the rest is really gibberish. And this is because we have not pre-trained our model. So in the next notebook, we will pre-train it, but this is why things don't make sense yet. It's normal, but now we have a way to generate text. Let's clean this up a bit. So let's maybe do it like this. Let's move this maybe here, so we have it all in one cell. Okay. And if we want to decode this, we add this. So this would be basically how we use the LLM to generate new text. So let's try this again. Let's just generate 5 maybe. Not quite. Something is. Oh yeah. Yeah, and so in the next notebook, we will actually train this network, and then it will learn how to generate actually more comprehensible text. But in this notebook, basically, we went over the whole idea of how an architecture looks like the overall concept, and how it's used to generate one word at a time. I hope it was informative. I know I skipped over a lot of architectural details due to time reasons, because I think this was another half-hour segment, so I didn't want to make this like a 20-hour course, but I hope this was useful. So next, let's go to the pre-training. Yeah, so now let's go from the architecture coding to the actual pre-training. So notebook 4. Pre-training LLMs. Again, this is a very abbreviated one, but I hope it will teach you the basic fundamentals that go into the pre-training. In case here, a very small GPT-2 model. So for that, to make it a bit faster, I will actually use GPU. Of course, everything also runs on a CPU. It will just be taking longer. So I recommend using a GPU for this particular notebook. So usually, it takes a few seconds to request it, but then we don't have to, there we go. We don't have to reinstall anything. It should all be still there, and all our data should be still there. So it's just loading this. And in particular, we will be talking about the pre-training and the training loop here. And this will be using the architecture we implemented in the previous section. The only modification I made is I made the context length a bit smaller. Originally it was 1024, but I thought, this would take a bit longer. Actually, let's why not do it? Let's just do it. Okay. But if you're running on a CPU, maybe use 256. So it's something we already covered. We are initializing the model like we've done before. And here's just a brief recap of what we have seen before. So we had some text. We tokenized the text, got the tokens, put that into the GPT model, and then it outputted this gigantic tensor. What we did then is we extracted the last value, so the last row here, and converted these then into the token IDs. So that's what we get here. So this is for the whole text generated, and then we use the tokenizer to convert the token IDs back into text, which gives us the actual text here. So this is what we have done before. And now we are actually training the network, because we've seen before it was not really giving us anything useful. What it was just gibberish. And for that we will be using also two convenience functions, text to token IDs and token IDs to text, so that we don't have to retype this every time. So these are two convenience functions that we can then plug into our generate function that we used and implemented in the previous notebook. So far it's only just adding convenience functions. Let me actually execute this. So this is essentially the solution that we implemented previously. There's nothing new here, except that we made this a little bit easier here, or more convenient for reuse. And you can still see it generates gibberish after the input. So we have to now train the model to kind of improve it. So for that, we will be using the same data set that we used in the first notebook, the verdict, this short story. So let's just prepare it again here and read it in. So it's again the exactly same stuff we have seen in notebook 2 here. So nothing new, that's why I'm going through it so fast. And the data loader, what it does is, the data loader prepares the data set so that we have batches for training. So if we have this whole input text, we would then tokenize this input text and then use the first, let's say, chunk here as our batch input, and then the second chunk is the second one, and so forth. So this is how we would prepare our batches. And of course, I'm only showing you that for a very small size, length 6. In our case, we would make the length a bit longer. We can use up to 1024, which is our context size. So maybe going up one more time. So before we set the context length here, and we can use that same number for our data loader so that we can process more tokens at a time. So if I scroll down again, sorry, lots of scrolling here. So we can actually, when we implement the data loader here, we can set the supported context size or length here as the max length, which will determine the length of these text chunks. So one other thing I should mention is we also divide the data set into a training data set and a validation data set. So here in this case, we don't have a test data set, but we can also use a test data set. But to keep things simple, it's only a training and validation set, and we can actually use a new data set as test set. But we will be revisiting the model evaluation later in more detail in this fine-tuning notebook section. So I have multiple notebooks. I think 2 or 3 of them are on model evaluation. So we will be revisiting this later. Okay, so let's now load the data set, reusing things we covered already. So I don't have to, let's say, go into too much detail here, but just to visualize how the batches look like. So we have a batch size of 2. So there are 2 inputs in each batch, and the size, the text chunk size is 1024. And the same is true for the validation set. So this is, actually, the problem is with 1024 is that the data set is too small. And so because we only have so few tokens, if we use 2 batches, we use all the batches up for the training set, and we don't have validation tokens. And this, now I remember, this is why I set it to 256 here. But I can also actually do this. I could do this also in the data loader. Let's go here. I could overwrite it here, just here, 256. Up to you, really. And the stride should be similar. Okay. Yeah, that looks better. So we can see we have 1, 2, 3, 4, 5, 6, 7, 8, 9 batches in the training set, and 1 batch for validation. It's a very, very small data set, right? So in reality, we would train the LLM on trillions of tokens, but yeah, this would take quite a long time. So we are only using this relatively small short story, which should train in a few seconds on a GPU, because I don't want to bore you here too much by waiting for the training to finish. So yeah, to count the number of tokens, we have 4,000 training tokens, 4,600, and 512 validation tokens. So in total, we have 5,120 tokens. And before training, it's always a good idea also to calculate the initial loss. So I'm not going to go over the calculation for the loss, but it's essentially a concept. The higher the loss, the worse. We want to minimize the loss essentially. So here I have a convenience function, calculate loss loader, which will calculate the loss based on the whole training set or the whole validation set. So here we have an initial loss of 10.9, which is really bad actually. So we want this loss to go towards 0 when we are training the model. So the model training is very similar to how we train deep neural networks in general. So we would iterate over the training epochs, and then we would iterate for each epoch over the batches in that epoch. We would, like in PyTorch, reset the gradients from the previous batch iteration, calculate the loss, do backpropagation to calculate the loss gradients, and then we use the loss gradients to update the model weights. And this is essentially number 6. That's the step where we update the weights, and that is how essentially the model learns. And the model will learn to minimize the loss based on these loss gradients. Essentially, it's the negative gradients. So I'm just saying gradients for simplicity because that's what people use. But we take a step into the opposite direction of the gradients to minimize that loss. Otherwise, we would be maximizing it. And then, usually it's a good idea to print out the intermediate values so we can see if our model makes progress during training. Because if it doesn't, then it's also always a good idea to maybe stop the training and change some hyperparameters and see if we can fix that. And then at the end, I also find it useful to print out some generated text so that based on the generated text, we can see how well the model performs. So my training function looks like as follows. Basically, what I've shown you in the picture is encoded here. So we have a function that accepts the model, the training order, validation order, and so forth. And here I'm iterating over the epochs. For each epoch, I put the model into training mode, and then I iterate over the training order here. So here I calculate the loss batch. So basically the loss for a single batch in the training set. Then I calculate the gradients, the loss gradients, update the model weights, and also for visualization purposes, I'm counting the number of tokens I've already seen. And this is really here just for tracking. So here I'm just collecting the data so that we can actually plot the training and validation losses after it has finished. And then also after each epoch, I'm printing out some sample text that the model generates so we can see visually if the model makes progress or not. So let's actually try this out. So here I'm setting my random seed, so it should be reproducible. I have my model, and I'm putting the model onto device. So device can be CPU or GPU. If I go up here again, I defined this. I think I skipped over it before. And so if you are running this on a GPU here or on your own computer, this will, if it's an NVIDIA compatible GPU, this will automatically run the code on the GPU and otherwise the CPU. So you don't have to do anything here. It will automatically take care of this. So it puts the model on the target device, either CPU or GPU. And we initialize also an optimizer. So in this case, we use Adam W, which is Adam with weight decay, which helps a bit with overfitting. It's not a bad idea. Especially because we have such a small data set. Also, in reality, usually, I could have maybe used a bit bigger data set, but in reality, usually we only train LLMs on, let's say, for one epoch. So only one iteration over the data set. But here, because it's such a small data set, I use 10 epochs to show some progress, basically. But if you have a larger data set, so remember the exercise from Notebook 2, if your data set is larger, you probably can reduce the number of epochs here. Okay, so let's actually run this and see what the results are. So by the way, there are a few more settings here. There is the eval frequency. That's basically how often the loss is calculated for the validation set. And yeah, so it's essentially, if we look this up again, eval iter. Sorry, this is actually in the function I was hiding from you. This is essentially for, let me see, eval iter, let's see. This is for the evaluate model function, which I've not shown you. I've hidden away some of the functions because I don't want to make this video too long, but there is, this eval iter, which means that it is only using 5 iterations from the training loader for the loss calculation for evaluation. Because if you have a large data set and you calculate the loss on the whole training set, all the batches, this can be a very, very expensive computation. So here we are just approximating the training loss by only iterating over it a fixed number of times. And in this case, this fixed number of times is by default 5. If you paid attention, our validation set only has 1 entry. So in this case, our validation set loss is calculated by only 1 validation batch. Okay, so here we can now see what happens during training. We can see that the training loss goes down, which is nice. So it goes down from 9 to 1. The validation loss also goes down. It starts at 10 and it goes to 6, but then it really stops improving. And that is really because, because the model is overfitting. It's a very small data set. You can see training loss is much lower than the validation loss. It's because we really, we train for 10 epochs. If we would train for fewer epochs, we would see less overfitting. But what we can see is that the model learns how to generate coherent text. So in the beginning, we have some really nonsensical text that's generated here. And then once we go further, we can see that the LLM becomes more coherent. So we can see at the end, it is actually quite coherent text. Actually, let's just search for this in the data set here. We can't find this one, but it's almost the same. You can see, yes, quite insensible to the irony. Here, oops. It's quite insensible to the fact. So it is kind of like memorizing to some extent. It's not too bad. But in practice also, there are more sophisticated generate functions. I'm not covering it here in this workshop, but let's say in my book, for example, I talk also about different methods for preventing this memorization during generation. So in practice, even if you have something like that, in practice it's not too bad because you would use something like top K sampling, for example, or temperature scaling. So this was the model training. It looks quite okay. Let's just save the model so we can instruction fine-tune it later. And let's also, in addition, visualize the losses. So I just showed you it before, like looking at the text, and here I'm looking at the losses. It's quite interesting. I have maybe changed something in the notebook because I haven't seen this peak before when I ran the notebook. So some of the things I've done while I was explaining must have affected this. So there is some peak here now, but you can still see after this peak the loss decreases, and we can also see the validation loss. It goes up quite a lot and then it converges back down. It's quite interesting to see that I must have changed something somewhere. And so this would be the model training. So what we have accomplished so far is that the model can generate text. And here, so just a small exercise. Try to use the text generate simple function we used before to just generate some text that is not from the book. So maybe pause the video and implement this exercise 1, and then I will show you the solution. Okay, so how I would approach this is I would just, because I'm lazy, I did already a lot of coding in my day-to-day. I will just copy and paste this and would just insert it here and hope that it works. So just making sure I'm not reloading the model. I don't need this. So let's just reuse this context here and see if our trained model is now better than before. Oops. All tensors must be on the same device. Oh, that is actually an interesting one. So what we have to make sure is that the input tensors are on the same device as the model. So what we forgot here is we have to do a to device here too. Okay, so yeah, it is generating more coherent text. Let's try something else. So it is kind of working. It's not perfect, but it is generating somewhat coherent text. So the next section, we will actually use pre-trained weights. I will show you how to load pre-trained weights, and then this will improve. Because yeah, you have to keep in mind our model has only learned from this one short story, which is in fact really short. Yeah, so maybe as a second exercise, try to load this model now in a new session, because this is also, I think, relevant, because here we are training a model, and let's say we want to reuse that later. How do we actually do that? So maybe pause that video and create a new notebook and see if you can load this model. So again, how I would do this, I would make a new file. Let's call this exercise 2 IPython notebook. Where is it? Oh, here. And then let me just try the naive thing. So I would say, where did I save my model? I saved it as model PTH. So I can do PyTorch, torch load, and then I can try to load this file. I can actually copy the path. So this would be loading my weights. And we have to also define the model. So what we have to do is we have to load the model. So what I need is essentially this part. And for this part, I need the model itself. Where did I import it? So or instead of scrolling, I could also look in this file. GPT model, I think, right? Yeah, GPT model. So let's say from supplementary import GPT model, and then let me copy this configuration. Okay, and then this should be fine. I have my weights loaded here. I have the model loaded here. Oops, device is not defined. You can just say device CUDA in this case. So it's printing the architecture, which is nice, but we don't want to bloat this notebook. So I have my model now. Actually, a good sanity check would be to copy the text. Where is it? To copy this section here. And see if it can generate coherent text. Oops, all tensors on the same device. I think, yeah, that's the same problem we had before. To CUDA. So right now we are only using the randomly initialized model, so this is not generating anything useful yet. So what we have to do now is we have to take these weights. I think it's model from state dict. No, I think this would give us I think it should be like this. Model load state dict, and then we will give it the weight. I think this should work. All keys matched, that looks good. And let's try it again now. Yes, so this is now using our pre-trained model essentially. Okay, so we completed exercise 2, and optionally exercise 3 would be training training the LLM on your favorite texts. And this would then conclude the pre-training section. Next, I will actually show you how we can load weights that are better than the weights we loaded here, so that the LLM can actually generate something that is even more comprehensible. So now we have a model that can generate some text, but it's not great. And that is because we only trained it on a very small data set for like a minute or so. And so the next notebook, we are going to load the pre-trained weights from OpenAI. So here in this notebook, we are loading them of how OpenAI originally trained the GPT-2 model. And yeah, back then they spent months and months on training this model. Today, with modern hardware, you can maybe train it in a week or so. But yeah, this is a much more capable model because it has been trained on, I think it was like about 500 billion tokens. And yeah, in this notebook, we are going to load the weights from that training run, the original one, into the architecture we just coded. And yeah, for that, we need to use TensorFlow. And that's because back then, yeah, OpenAI used TensorFlow. And the code will be still PyTorch. It's just required here for loading the weights from the original files that are provided by OpenAI. So I'm importing here this download and load GPT-2 model. And this is a function I implemented and tucked away a bit because it's not super interesting. It's essentially just downloading the relevant files from the OpenAI website, this OpenAI public prop core so-and-so website. And this contains a bunch of files for each model that we will use to load the model. And so essentially it's just loading the parameters and the settings. So yeah. So this is essentially, I would say, not super interesting to go. Also, actually, I'm using this one, settings and parameters. So it's just loading those. And if you are running this in the studio, it will actually be quite fast. So this will be only taking a few seconds because I already downloaded these files for you. If you're running this on a laptop, it might take a few minutes, but shouldn't be too bad because it's a relatively small model. Using this function, we implement or we download this settings and params that are prepared with the function I implemented there. And just to show you briefly what those variables are. So settings are containing information about the architecture. So this is similar to what we had. If I go back maybe to, let's go to notebook 4. It's similar to this structure here. The naming conventions are slightly different. So I call it context length instead of, NCTX. Thought it's just a bit more readable. But otherwise, the number of heads and number of layers, it's basically the same convention that we used here. Okay, so this is where these names come from. So it's just like the general settings. The params here, they do contain the contents of the weights, the tensors. So this is a dictionary that contains the transformer blocks. And this, I think, is a bias unit for the output embeddings. These are, I think, the variables for the layer norm, the final layer norm. This is the positional embedding layer and the word embedding layer. So the first token embedding layer, TE for token embedding, and PE for positional embedding. So they would correspond to, if I go to the architecture here, let's see, they would correspond to this. First, WTE would correspond to this one, and WPE would correspond to this layer. And then the G and B, I think they correspond to this final layer norm. It's been a while since I wrote this code, but the way you can tell if you do this mapping correctly is if you load the weights and you make a mistake, the model will not be able to generate anything useful. So a good sanity check is really just loading the weights, seeing if the model generates coherent text, and if it does, it's usually meaning that you did this mapping correctly, because the model is very, very sensitive to the correct numbers there. And we can actually take a look at some of these contents. So let's maybe dive into the blocks. So the transformer blocks here, that should be a list. Let's see. Oh, sorry, I wanted to say length params. So there's a length. Oh, it's 5, also 5 content. Sorry, I wanted to take a look at the blocks actually. Yeah, speaking and typing is for me somehow challenging. So there are 12 elements because we have 12 transformer blocks. So if we take a look at the first transformer block here, index 0, let's see how that looks like. It's actually a dictionary, I think. So let's do keys. So this contains the attention weights. There are 2 layer norms and this MLP, which stands for feed forward, like it's a multi-layer perceptron feed forward type. So the first layer norm, the second layer norm, and then this MLP is this feed forward part, which itself consists of 2 fully connected layers. So I think I had here a better figure. So you have one linear layer and another linear layer and an activation function in between. But activation functions don't have any parameters. So we only have basically parameters of the linear layers here. So let's take a look maybe at one of those. So I do MLP here and then maybe keys again. So right now I'm basically looking at the 2 linear layers in the first transformer block, so linear 1 and linear 2. They have a bit of a weird naming convention, but yeah, that's basically how they named them back then. And let's just maybe look at this one. Oops. And I think this is also a dictionary, so let's see. So and this has both a bias and a weight matrix. So these are the weights and this is the bias vector. So we can actually take a look at the weights. So these are the weights and they are in shape or dimension 768 times 3072. So the number comes from this embedding here, the embedding size, and then it's projected 4 times larger. It's maybe hard to see here because we haven't coded the whole LLM because I was trying to avoid this because it would be otherwise too long. But I think I should have it here somewhere. Transformer block, feed forward, yeah. So you can see the embedding size 768 is projected up by 4. So if I have 4 times 768, I should get this 3000, what was it, 72 here. So that's where these numbers come from. So now my challenge is basically, or my task or my problem is, how do I get these weights into my model? So how do I really get those into my architecture that we coded? So yeah, I actually wrote a function for that too. So let's first load the model again like we've done previously. So this is the model we coded and I have different configs here. So this would be the 124 million model that we just loaded. So if we take this one, so the mapping here, if we take this one, we initialize the GPT model right here with a 124 million size. So the way why it looks so complicated is, it allows you basically to swap the model out. You can use, for example, the larger model here if you want to. Okay, we also have to enable, so this was the config we used previously. Let's say we used a smaller 256 context length as we did for the small data set. We would have to increase this because the original model was trained with that context size, and this is to make the positional embeddings to match. And I think I mentioned this before, but originally the researchers also used bias vectors for the QKV matrices. It's really not necessary and not recommended, but they did it back then. And if we want this model to work well, we have to exactly match what they've done. So if we want to load the weights correctly. So that's why I'm also setting these here. And yeah, then I'm initializing this model and have a small utility function. So this function is really just making sure the shape of the left tensor is the same as the right tensor if I give it 2 tensors, and then it will convert the tensor into a torch parameter. So we'll call torch tensor and then torch parameter to convert this basically. And then it's really, this is like a tedious part I've already done, but then it's really like a brute force finding out what does the name they provide, like C projection, what does it correspond to? Is this the first or the second linear layer? It's a bit tricky, but actually you can do it by trial and error because you know what the dimensions are. And you will also see if you do a mistake here, the model won't produce anything useful. But yeah, I've already done all the hard work here, so don't worry about it. But yeah, so this is essentially a utility function that loads the TensorFlow weights into PyTorch tensors, which then are used by our model. So I have this utility function here that I'm calling that really uses this mapping to load everything into our own model. So it's, yeah, a brute force thing where we have, let's say, so here I'm iterating over the transformer blocks. And if you take a look, let's not look at the attention because we haven't covered this really, but let's look at the fully connected layers, the linear layers. So here I'm, let's say, in transformer block B, and I'm assigning here in this attention part the left one, to the right one. So basically I'm taking the OpenAI weight and overriding it with our own weight, basically. Also, the other way around. I'm taking my own weight and I override it with the OpenAI weight. And I do this with every single weight here. So for each single weight, I'm overwriting my randomly initialized parameters with the OpenAI one. It looks very tedious, yeah, but if you do this for all the weights, then the model should be initialized with the OpenAI pre-trained weights. It took me a couple of hours at least to figure out the right mapping. It's not a fun exercise, but once you have done it once, you never have to do it again, for this model at least. And now we will be ready to use the model. So now we have the pre-trained model, and I'm using the same function we used before, this generate text simple, giving it now the model with the loaded weights, and I'm giving it the same input again, and let's see what it produces. So yeah, it produces more coherent text, or not coherent necessarily, but more text that matches what we've provided here. If I maybe modify this a bit, moves you forward. It's kind of like the same. Okay, every effort moves you forward, then you move forward. The first step is, we can actually maybe extend this a bit. Okay, it's very repetitive. And this has also something to do with the fact that this is still a very small model. Okay, it's kind of repetitive. So as an exercise for you, I encourage you to try a larger model and see if this can actually improve the quality. So maybe pause this video at this point and see if you can modify the section above here and use a larger model and see what you get. Okay, so let's maybe use the one next larger model. So let's use this one. So I should also make sure actually I download the larger model here. It shouldn't be too long, but yeah, it's 1.42 gigabytes. Maybe should have saved them here for you so you don't have to do this, but yeah, it's all good, I think. Yeah, it's sometimes tricky to plan a very long, coding session. So I think when I'm finished with this, it's probably going to be 3 or 4 hours. And, ideally in an ideal world, I would probably go back and polish it up a bit and then redo it. But, a day only has so many hours. Okay, so it's downloaded now. And let's go here to this part. Sorry, where was I? Lost the overview a bit. So here, I have the 355 that I'm loading now. So this will be the randomly initialized model. We already initialized these parts. We don't have to do anything here. And here though, yeah, we need this basically. So we will need to execute this, which will be loading the pre-train weights similar to before into our model. So it was pretty fast actually. And now let's see if this will look any better. Well, it's somewhat better. Every effort moves you forward, but you must be careful. You must not let your guard down. You must not let your guard down. It's a bit repetitive, and that's like, okay, that's already better. Every effort moves you forward. Yeah. So it is a bit, it's not great. It's a bit repetitive because we're still working with a smaller model. If you should use this one or should happen to use this one, you will see it will be much better results. But yeah, we don't, I would say, have that much time here to download the weights. So I don't want to bore you. I can leave it as an exercise. So yeah, I personally like doing from scratch stuff a lot because yeah, it's fun for me, but it takes a long time. So for this workshop, for the remainder, I'm actually gonna use a library called LitGPT so that we can make some progress here. So LitGPT is kind of based on the same concepts that I've shown you before. It's a library I helped developing. It's more sophisticated though. It's it's implementing some more optimized code and also supports a lot of other LLMs besides GPT, but I can maybe briefly show you how it looks like. So here in LitGPT, basically, there is this model here, model PyFile. And for this one, you can see it's also a GPT model. So all the other models like Llama, Phi, Gemma, they are derived from that. So here, this is implementing the base model. But then when you look at the config, that's where you would basically set the different settings. For example, let's see, stable LM, you would then set the different embedding sizes, number of heads. Some other LLMs have different multi-layer perceptron parts. Let's see if we can go to Phi 3, a recent one. So this has also some other modifications. For example, the number of layers and different things that you have to tweak. But fundamentally, it's not that different from what you would see when you implement, like GPT type models. It's essentially all based on the same architecture. For example, here Mixtral is a mixture of experts. It's slightly different, but still you have the concept of block sizes, number of layers, and so forth. There's something called n-query groups, which is multi-query attention. It's essentially just a small modification where you, instead of having one value key query connection, you have for each query you share the key and values basically. So it's essentially just like little tweaks, but nothing fundamentally different. So here in this notebook, I wanted to just briefly show you how you can use LitGPT to, let's say, use more sophisticated LLMs other than GPT-2. So there are multiple commands. There's a command line interface, LitGPT download, LitGPT chat, evaluate, fine-tune, pretrain, and serve. And for this notebook here, we will be just looking at downloading and using the model, for example, LitGPT download and chat. You can install it via pip install LitGPT. If you are using this studio, you probably don't have to because I already did it for you. But if you are running it on your own computer, you just do pip install LitGPT and it should be all ready to go. And so as I mentioned, there are a couple of LLMs implemented. So you can actually get a list by LitGPT download list. It gives you a list of all the LLMs implemented in LitGPT. So it's a very long list. Let's say we are interested in Phi 2. I'm actually not running this command because I already downloaded it for you. So it should be here in the checkpoints folder on Microsoft. So you don't have to download this model if you're running the studio, but if you're running it at home, execute this terminal command. There is also a Python API. So if you want to use LitGPT in Python for generating text, you can also do that. So here I'm importing the LLM class from LitGPT, and then I'm loading this model that I just downloaded here. So let's do that. So it's loaded now, and now what we can do is we can do llm.generate. Let's say asking it a question here and see what it responds. Yeah, so that's like a response to what LLMs eat. We can also stream the response, which means basically instead of generating all this text all at once, it will do it one text or token at a time. Yeah, and then just for fun, a small exercise, you can try to download another LLM. For example, Pythia, Llama, Phi3 maybe. Maybe Phi3 might be a good one because it's a quite new and good model. So how you would do that is, let me just use the terminal. It's a bit easier than doing these things in a notebook. LitGPT download, let's say grep Phi. I forgot. Should type list here. Yeah, it's just something I recently added, I don't know, 2 days ago, so I kind of forgot. Okay, so we can then maybe also download this model. LitGPT download Phi3. Spelling is a bit different. It's the way Microsoft uploaded these models. It's with a capital letter. Here it's with a smaller case letter. It's kind of a bit inconsistent, but it's what it is. So yeah, it takes a bit, but shouldn't take too long. So this is basically downloading the weights and the config files. And then it's converting the weights into a LitGPT compatible format. So first it's converting the safe tensors to bin files, which is a bit easier to parse. So because some have safe tensor files and some have bin files. And then now it's loading the weights. And yeah, I'm very proud of this progress bar that I just added the other day. So it's showing you the progress, how long it takes to convert the weights. And then they are converted. And yeah, this should be then saved as one file. So it's saved in this folder as I think it's litmodel.pth or something like that. Let me double check. I always forget the name. Not that it matters, but yeah, just showing you. So you can now find this model here. And then this would be the LitGPT compatible weight file. And then I can load this. I kind of forgot the name. Let's just put it here. I'm out of memory because yeah, I still have the old Phi model in memory. But you could also do what I could have done instead of restarting the notebook. Could have just deleted LLM and then loading it, because when you have this object here and you call load in Python, it will load it and then assign it, so you had for some amount of time 2 LLMs in memory. Okay, so let's try this model. Yeah, it's also a relatively reasonable response. Yeah, and this is essentially how LitGPT works, and in the next notebook we will be fine-tuning it. Okay, let's now move on to part 6, instruction fine-tuning. So there are multiple ways we can fine-tune a large language model. One is, for example, classification fine-tuning, and another one would be instruction fine-tuning, where we provide we create a data set with instructions, and then the large language model learns to answer questions or follow instructions. For example, convert the sentence from active to passive voice or passive to active voice, or fix the grammar in the sentence and so forth. For this one, we are not going to do it from scratch because this would take a very long time. But if you're interested, I have a notebook here with detailed notes. So this would be implementing the instruction fine-tuning process from scratch. You can see it's a lot of code, which might take 4 to 5 hours to walk through slowly. So in this case, we are going to use LitGPT in the next two notebooks, but I wanted to at least give you the introduction to instruction fine-tuning, how the data set looks like, because I think this really helps understanding what's going on when we talk about instruction fine-tuning. So yeah, just to give you a few more examples of instructions. So here on the left-hand side, I have 3 examples. Convert 45 kilometers to meters, and then the desired response that we want the LLM to generate would be, in this case, 45 kilometers is 45,000 meters, or provide a synonym for bright. In this case, a synonym for bright would be radiant. And here another one, edit the following sentence to remove all passive voice. And then we give it the sentence, and then here we have the sentence converted to active voice. So on the left-hand side are examples of instructions that we would feed to the LLM. And then on the right-hand side, these are the desired responses. So the LLM should respond in this way or in a similar way. It doesn't have to be exactly that way, but it should be, of course, answering or fulfilling the task here. So for that, I have prepared a data set. So I created it myself. I just called it instruction data. So let's take a look. So this is basically a JSON file here. So here I have a bunch of instruction entries. So here each entry consists of an instruction key, an input, and an output. So the input is the instruction, and then I have for example, evaluate the following phrase by transforming it into the spelling given. It's kind of like a weird one though. Okay, let's take maybe this one. It's easier to talk about. Edit the following sentence for grammar. And then we give it the sentence as input, and then we hope the LLM will generate something like this, where it corrects the grammar. So here it says he go to the park every day, and one correct way would be he goes to the park every day. So it's correcting this spelling here, or grammar. So some of these examples don't have this input though. So you can see here I have an instruction that says convert 45 kilometers to meters, but there's no input field. So in this case, the input is kind of like part of the instruction. So there are these two forms of instructions. And the reason why it's formatted like that is I took the Alpaca dataset as an example, which is, I would say, one of the early, really popular instruction datasets. And I just followed the same style, just for historic reasons. And in that case, some of them had inputs and some didn't. So in practice, you can actually also get rid of the input field and always include this as part of the instruction. You could do something like this, for example, and then just get rid of this. But I included it for historic reasons here because that's like the original, let's say, way of doing it. We can count this. We have about 1,100 instructions here. And this is like, I would say, a relatively small data set. Originally, Alpaca was about 52,000. And later papers like Llama, I think it stands for less is more, showed that you can also get really, really good results with only 1,000 examples. So there they focused more on high quality instruction inputs and longer inputs, and found that with 1,000 instructions that are high quality, you can actually beat a model trained on 52,000 in Alpaca. But then also you can also think about it. Okay, quality is key, but you can also think about then, okay, why don't I make 50,000 high quality instructions, right? So there are several data sets available on the internet. I think that maybe hundreds or thousands of these data sets. Some even have 500,000 or so instruction inputs here. So to make the training relatively fast for this workshop, I have a very small data set only consisting of 1,100 and relatively short instructions just to accelerate the training a bit. So let's load this data set. So we have 1,100 instructions, as I mentioned. And each training example is like a Python dictionary. And you can see there's an instruction field, an input field, and then an output field. And like I mentioned before, some have a blank input field. Now, this is how a dataset entry looks like, but this is not how we would typically feed it to the LLM. Because if you used, let's say, ChatGPT before, you know that you're just providing the LLM with natural language. You're not using any, like programming, formatting characters or something like that. So in that sense, what we do first is we convert this instruction into like a human, let's say, written text or something that looks more natural. So in this case, I'm showing you an example using the alpaca prompt style template. So what it is doing is it's converting this input or the whole entry into a human-like, text. So here, what it is doing is prepending something like a boilerplate, something like below is an instruction that describes a task. Write a response that appropriately completes the request. So it's giving the LLM more context of what we wanted to do, and then we format the instruction here. So we have like a header, like these 3 pound signs, and then instruction, 3 pound signs input, and then the response. So this would be a formatted training example. And here on the left hand side, I'm using the alpaca prompt style, which was, I would say, one of the first popular prompt styles that were used. I'm using that for historic reasons, but you don't really need all of that. So you can make it actually also simpler. For example, in Phi 3, they have something that's more like this, where you have a user and assistant tag. Instead of using instruction, they use user, and instead of response, they use assistant, and they don't have any boilerplate. So I also tried this out with the same LLM when I instruction fine-tuned it, and you get approximately the same performance out of the LLM if you use this style. And what's nice about it is it uses less resources, because here you can see this is much more text. So the LLM needs larger text input, which requires then of course more memory. So in this case, this is even more memory efficient. But I'm using alpaca style here because that's the original. That's, I would say, the most popular one. So here's some code that formats an input in this alpaca style, and you can see how I deal with the input. So I say provide the input if there is an input field, otherwise leave it blank. So maybe it's easier to just show it to you. Let's see. So here is how the model input would look like. That's without the response. This is what the model, let's say, will see when we wanted to generate stuff. And then also adding the response here. So the complete formatted example would look like as follows, where we have here basically what I've shown you above here. So that's just the formatted prompt, some code for that. And if we don't have an input field, then it will skip it. So you can see there's only an instruction and there is no input, because in that case, if the input is empty, it will skip it. Okay, so we now saw how we can take this entry and format it into an instruction style. And then the next step would be tokenizing that. So this is going back to the very first notebook we talked about tokenization. So a long time ago, but we talked about converting things into token IDs. We use the same concept here. So we convert these instructions to token IDs. And then, so first we convert it into token IDs, but then we usually want to create training batches. And this is similar to what we have done before during pre-training. So let me see if I can spontaneously find the right section here. So here when we go back, we created these batches where each has the same length. And here it was easy in pre-training because we could just chop it up like that. So where we could define a certain length and then make equal length chunks and put them into mini batches or batches. So here it was relatively easy in pre-training to prepare the data set like that. But during instruction fine-tuning, each instruction input would have a different length. So how do we actually deal with that? So one way to deal with that would be to add so-called padding tokens, so padding tokens. And padding tokens here are, if you remember, it's a long time ago, but we had this end of text token. So we had this end of text token here. And here's where we are reusing this end of text token, which corresponds to token ID 50,256. So in the left-hand side, let's say we have 3 instructions formatted, and here we have the token IDs. Of course, they are very short because I wanted to fit it onto one image, but you know, they would be very long in reality. But if we assume these are my 3 different instruction inputs, you can see that instruction input 1 has 5 tokens, the second one 2 tokens, and the third one 3 tokens. So in order to make them all equal length, what we do is we are padding them. So this means we are making them all the same length here. And then if we have a different batch, we do the same thing here. But note that we don't have to have all the batches the same size. So the first batch can be longer than the second batch. So in this sense, we are just making sure that all examples in a single batch have the same length here. So you can see in this case, the longest example is 5. So everything is padded to 5 tokens. In the second batch here, the longest example is 4. So we are padding everything to 4. In this case, only the first example. So we are just making sure everything is the same length. And then when we create the the targets for training, what we do is also we create these tokens shifted by 1. And again, this is very similar to what we have done in pre-training. So in pre-training, I think I should have a figure here somewhere. Maybe it was in the previous notebook. Thought I had a figure on this. Let me see. Maybe it was here. Yeah, I think this is it. So if you look at this in pre-training, what we've done is we have everything shifted by 1 position. So we have the blue box, which is the input, and then the targets shifted by 1 position. And we do the same thing now for instruction fine-tuning. So here we have the input instruction, and then the targets are shifted by 1 position. So you can see that everything is shifted to the right. +1 would be the target. And then if we do that though, the targets will be shorter than the inputs. So we add also a padding token here. And what's nice about it is this padding token is this end of text token. So the LLM will then also learn, okay, this is the end of the text now, the end of my response. And we can use this token to also, when we create the instructions, to stop generating the response when we encounter this padding token. One more thing I wanted to explain is, so this is how the data looks like on the left-hand side, right? The formatted response. And we have then optionally these padding tokens, but also in practice, what can happen, or what is common sometimes is, so I should actually say we have an end of text token that we add. It's quite common, but then also what I should say is we typically mask out also the instructions when calculating the loss. I would say it's more like an optional step, but I did experiments, and there was actually also a paper showing that for shorter data sets, you may not need to do that, and it's actually better not to do it, but it's relatively common to mask out the instructions. So what that means is essentially that when we are calculating the loss for the LLM, we are only calculating the loss over the response. Otherwise, we do the same loss calculation that we do during pre-training, where we are calculating the loss over all the inputs essentially. So if I go back, where basically we have the input here, and then the targets, and the targets are just shifted by 1, and when we calculate the loss, we calculate it for every token position. And with instruction fine-tuning, it's often common to remove the inputs from the loss calculation, and how it can be achieved is by masking these by -100. But that's maybe too much detail because I'm not showing you the loss calculation. If you're interested though, I have a walkthrough here how it's done. But it's a bit more code, so let's maybe in this particular case not worry about these -100s. But like if you're wondering if we calculate the loss over the inputs, now you know that it is a research problem, that some people do it and some people don't. Okay, so this is in a nutshell how a data set for instruction fine-tuning works. And so next we will go over instruction fine-tuning in LitGPT. Part 2 would be the instruction fine-tuning with LitGPT. But before we go to the instruction fine-tuning itself, just a very brief note about a technique we are going to use to save, let's say, some compute resources to make it a bit faster and memory efficient. So there's a technique called LoRa, which stands for low rank adaptation. And so how it works is essentially we are approximating the weight updates. So if you think about any deep neural network. It doesn't have to be large language models. So you usually have some pre-trained weights or just the weights in the model. And then at each training loop, what you're doing is you are computing the weight update, how you are going to change the weights in that model. So here, this is the delta W. That's how the weights would change in each training pass. And if W, let's say, is a 10 by 10 matrix, then this would be 100 values, 100 weight values, and the weight update would be also 100 values here. So we have 10 times 10. Now in LoRa, we are replacing this weight update matrix by two smaller matrices that are approximating this. So for instance, assume if this is 10 by 10, then we would have, for example, something like 10 by 2 and 2 times 10. And 2 times 10 is 20, plus 20, we have 40. So we are kind of saving weights by using these small matrices compared to the original one. And if you think about, let's say 1,000 times 1,000, that's 1 million, right? And we have 2 times 1,000 plus 2 times 1,000, that's 4,000, right? So in this sense, we can save a lot of weights by using smaller matrices. And the inner dimension here, R, that's the rank. This is a hyperparameter. We usually use something like 8 or 16, but it's just like an example. And if this is like too complicated, don't worry about it. It's just a way of, saving some memory by approximating something. The LoRa layers, they're usually applied to the linear layers, the weight matrices, weight matrix layers that are linear layers. So, and in a neural network or in a LLM specifically, we would encounter them in the output layer in this feed forward module, the multi-layer perceptron module, which has 2 linear layers. And then the matrix multiplications, the QKV matrices in the masked multi-head attention modules. And we have that over a number of blocks. So there's actually a big improvement in terms of memory if we apply this to all the blocks in the model. So here in this section, we are now loading the dataset from the previous notebook, our 1,100 instructions. And before we start instruction fine-tuning, of course, like in every deep learning project, we should divide the data into training and test data. We also have a validation set later that is created by LitGPT, but here at least we are dividing it into training and testing data. So we will have, in this case, 935 trained samples and 165 test samples. And we are also saving them as JSON files here. Okay, so now we have this test and train JSON here. Now we are going to do the instruction fine-tuning, and instead of using regular instruction fine-tuning, we will use the LoRa instruction fine-tuning. But you can also remove that and just try the regular one. Depending on your hardware though, this is more expensive, and this might be, I would say, for this workshop to save some memory for smaller hardware. If you are executing this on your own computer, I would recommend this one. So here are a few settings. We define the JSON data set format that we are going to use. We use 10% of the data for validation, and we provide the path to the training JSON file that we created. And we train for 3 epochs and block the results every 100 epochs. So let's see, it might take a while because we are still, it's relatively efficient, but we are still training over 3 epochs. So by default, you will see all the hyperparameter settings. So added this for record keeping, so you can always see what's happening under the hood. We have only 2.6 million trainable parameters, and the Phi model has 2.7 or 2.8 billion parameters. And so you can see with LoRa, instead of training 2.8 billion parameters, we are only training 2.6 million, which is like, it's 1,000 less parameters, 1,000 times more, let's say, savings in terms of memory. Not memory, savings will be not that big in memory because the matrix multiplications usually itself take more memory than the weights, but we will save still a lot of memory, and we will save especially storage, because we only have to now store 2.6 million instead of 2.8 billion parameters. You can see the validation loss is NA here, and that is because the validation loss is only calculated every so many steps. So actually you can look this up here. Eval. So every 100 steps is, because otherwise it would be too expensive if at every step we would calculate the validation loss. So this will be first available after step 100. But we can already see that the validation loss goes down, which is great. So it goes from 2.2 to 2.5, which is actually great. Maybe we don't need to train even 3 epochs. That's actually already quite good here. But we will see. We can see it's still going down. We are in the second epoch now. So again, I used a very small data set so that this goes very fast. If you train, let's say, on the original Phi data set, on the original alpaca data set with 50,000 entries, it might take, I don't know, 3 hours or something like that. So in this case, to make it faster, I use my small data set here with very short entries. You can also see the maximum length of the training data is 101 tokens, where the model supports up to 2048. So in this case, you could have much larger inputs, but again, to make it more efficient, I used a very small data set here so that it will complete in a few minutes. So 100 steps have elapsed. So we should, next time it prints the line, we should see the validation performance. Yep, we can see 0.557, which is actually quite good. We had before 96, 557, but you can see there's a jump here. Oh, it's going down again. There was a slight jump in the training loss. I don't know exactly why. This can sometimes happen if it's a specifically challenging example. And so in this case, we can see validation loss is 0.557. Note that this looks identical because it's only updated every 100 steps, like I mentioned, for efficiency, where for the forward pass, we have to compute the loss or the predictions anyway, and then in the backward pass, we compute the loss for the updates. So in this case, this is, of course, for every iteration, where this is only for every 100 for just efficiency reasons. Yeah, we can see it's still improving, at least based on the loss here on the training set loss. Validation we don't know yet, so it could be overfitting. But it looks actually quite close, and that looks quite good actually. Not much overfitting at least. So about 213 seconds elapsed, which is 3.5 minutes, right? And we can see a validation loss is 0.51 and the training loss is 0.9. So in this case, it's actually not even overfitting, so it's about equal. And note that this is also an approximation, right? So this is only approximated on the current batch and not the whole training set, but we can see approximately that the model trained quite well here. Oh yeah, I already see this is the end of the notebook. So the next thing is actually an exercise for you. So we will be evaluating the model based on how good the responses are in the next notebooks. So here we are only looking at the loss, but we will also compute a score. And for that, we will save the test set responses because, like you know from other deep learning projects, we should take a look at the test set, which has not been used for training if we want to get an unbiased estimate of the performance. So here, this function, what it is doing is formatting the input for the model. And this is for, let's say, the test set. And so the task would be, I can actually delete this because this is something you shouldn't see. The task is essentially to generate the responses using the model for all the test data points. So here, so we can iterate over the test data set for E in, let's say, range test data. Should say length, and then for each of these test set entries, I recommend calculating the response by the model, model response, and then adding it back to this test data dictionary. So for that, you have to use the format input, right? Because otherwise, if you only use this, it will give you this, it doesn't even work, of course. it will give you this format, and we need actually for the model input, we need these two formatted in this fashion, right? Because that's also what the model has seen during training. So you have to apply this format input function. What happened here? Oh, format input. Here we go. So this would be the model input, and yeah, generate this for each test sample and then add this to the test data set, the model response basically. So the model, so maybe pause the video, I'm talking too much, maybe just pause the video and try to think about how to do that, because yeah, for that we will be using the LLM load method in LitGPT that we used previously, and then you can use LLM.generate to generate the response for this one here. So maybe I can just show it to you. But if we have the LLM loaded, you could be doing LLM generate like this to generate the response for the first test set sample. And the task for you is to apply this to all test set samples. Okay, maybe pause the video and then give it a try. Okay, so let me show you how I would do it. I would probably use a progress bar for, let's say, import TQDM. I think it's from, I always make this mistake, from TQDM, import TQDM. And then let's say for I in TQDM, and then let's say, what do I want? Range, right? Length, test data. I think this should work. Just thinking about, yeah, I think this should be fine. And then I actually need to load the LLM. Let me do that from LitGPT import LLM. And we are going to use first the base model, by the way. And then in the next exercise, we do the same thing for the fine-tuned model. So let's do LLM LLM.load, and then Microsoft Phi2. I like the Phi2 model because it's relatively small but capable. Okay, so let's load this one. Yeah, typos. And then here we should replace it with an I, of course. And this looks good. So we have test data I, and then how do we call it? Maybe base model, and then assign the response. So I think this should be correct. We'll see. And so right now I'm iterating over all the test data points, format the input, give it to the LLM here, generate the response, and assign the response to this base model thing. So yeah, this might take a while. So in the meantime, I could actually already, I just delete this. Already have a solution here. So let me now do this also for the next part. So LLM load. And for that one, we want the fine-tuned model, right? So I go up here and look what the file path is. So here it says where it's saving it. And so we need in LitGPT, we need the folder, similar to how we use the folder here. So we need the folder, copy this one. We can also specify a different folder. This is just the default folder. There's actually a setting for that. If you scroll up, output dir, that you can set. You can just, yeah, you would set it like this. In my directory or something like that. But yeah, for this example, I didn't specify it, so it's gonna be this directory here. And should probably delete the old LLM just to free up some memory. And then I can actually copy. Oh, that's already finished. Let's take a look actually. Test data. Let's just take a look at the first one. Oh, yeah. So we have the input, the output, and then the base model response. The car is as fast as a cheetah. Okay, it's actually a bit long, so it creates some other stuff here. Let's see if it's... Oh, here it looks better. So yeah, the name of, so we ask it the author name of the book, Pride and Prejudice. The correct answer is Jane Austen, and here it's a bit more verbose. It says the author of Pride and Prejudice is Jane Austen, but I would count this as a correct answer. So this looks good. Now, but this is the base model, so actually we don't expect it to be that good. And the reason is, I think, or many people think, Microsoft has actually fine-tuned the base model on instruction data, so which is why it's relatively good, but it's not perfect. You can see this is good, but then it has some other stuff. But it's actually a quite good base model. I'm surprised. Okay, but let's take a look at the fine-tuned model. So let's do this. I actually don't need this part. And then in the next notebook, we will be evaluating the models with benchmarks, common benchmark data sets, and then also another scoring function. So here we are just, eyeballing it. We are just looking at it and that looks good, that doesn't look so good, but it's not very quantitative, right? We are just, looking at some outputs and eyeball it. I think people, I don't like that term, but some people call it vibes. So it's like, perceiving how good a model performs. Yeah, there's a lot of, if you haven't noticed, there's a lot of jargon in the large language model field. Okay. It's actually quite, it might, you might think it's taking a long time, but it's actually quite fast. I'm actually quite impressed how fast it goes. Okay, let's take a look at some fine-tuned response data. Let's take a look at the first example again. Yeah, see, this is actually already improved. So you can see the input is the car is very fast. The output is, the desired output would be the car is as fast as lightning. But this is only, one possible example. And the base model generated the car is as fast as a cheetah, and then has some other, stuff here, where the fine-tuned model is actually more concise. It says the car is like a bullet, which is actually quite nice. It's like a very nice and concise one. And you can see it hasn't memorized anything. This is the test data, so it hasn't seen the test data, but it's also using a different response, but I would also count this as a correct response. So the next notebook, let's just take a look at some common benchmarks, and then we will develop a scoring way of doing this more quantitatively instead of just eyeballing it. Yeah, so in part 3, we are going to take a look at some benchmarks, some ways we can calculate the performance of LLMs based on popular benchmarks. One such benchmark is MMLU, which stands for Measuring Massive Multitask Language Understanding. And every time there's a new GPT model, or what is the other one, Anthropic Claude model, or Gemini model, there is usually a technical report with an MMLU score. And this measures essentially the knowledge of the LLM based on multiple choice questions. I would say multiple choice question answering is not the best way to evaluate LLMs, because it's testing the knowledge, but it doesn't really test how well it generates text. But in any case, so how it works is essentially there is an input, for example, which character is known for saying to be or not to be. That is the question. And so four potential answers are Macbeth, Othello, Hamlet, and King Lear. And then the model gets this input and has to respond with a correct answer. In this case, the correct answer would be C, Hamlet. And then we will check if the answer is correct. And if yes, we compute this as a score, and then we divide the total number of scores by the number of examples, multiply it by 100% to get accuracy. So what it means is essentially 90% accuracy means it has 90%, has answered 90% of the questions correctly, for example. So this would be one way of evaluating LLMs. And there's a tool called the Eleuther AI LM Evaluation Harness, which essentially does the same thing, but also for different tasks. So it's actually a really nice tool which integrates multiple methods. So here I'm just showing you an example in LitGPT how we use the Eleuther LM Evaluation Harness to compute HELLA swag, truthful QA, and MMLU scores. This would be one way of getting performance estimates for an LLM. Another one is Alpaca Eval. So Alpaca Eval is a leaderboard where the developers of that leaderboard compare models to GPT-4 preview. So if you have a model and you generate a response, they use a GPT-4 based, let's say, judge or auto annotator, and they ask that GPT-4 model, how does this model response compare to GPT-4 preview? And then it gives you a win rate, and this means basically GPT-4 Omni wins 57% of the time compared to GPT-4 preview. And then something like the original GPT-4 model, it only wins 38% of the time compared to the GPT-4 preview model. So it's essentially like a relative benchmark compared to how a model compares to GPT-4 preview in terms of its response quality. Another popular benchmark, I think it's maybe even the most popular today, is the LLMs chatbot arena. So how this chatbot arena works is it's essentially crowdsourcing the evaluation. So I can actually maybe show this a bit bigger. So here what you do is essentially you have two models, let's say Gemini and Phi3, and then you are comparing, so you're giving it the same answer, the same response, and then you're comparing the answers. So there's model A, Gemini, model B, Phi, and both get the same instruction, but both, of course, generate different answers. And then as a user, you can say A is better, B is better, it's a tie, or both are bad. And based on this ranking, the people at LLMs chatbot arena calculate a leaderboard then, and then you can see how the model compares to other models. And I think this is actually a really nice benchmark because it asks people actually how useful do they find a LLM, how good are the responses. Of course, it's not perfect because for knowledge-based questions you still need to know the correct answer to give a correct rating here. So for example, I don't know, if you ask it who was the first president of the US and it gives you a wrong response, you have to know that this is a wrong response to give it a bad rating, right? So in a sense, it requires humans to also know the correct response, but I think it's still quite a nice way of evaluating LLMs. So in this notebook, I will go over how we do the MMLU evaluation, and then in the next notebook I will show you an automated way that is more similar to this Alpaca Eval. Okay, so actually I may have accidentally deleted a few cells. So let me just do this off the top of my head. So in LitGPT, how we would get the scores, I would just do LitGPT evaluate list, and then so this would be listing all the tasks that exist in the evaluation harness, the Eleuther AI evaluation harness. Yeah, it's a bit ugly because we installed TensorFlow at some point. So this is a very long list of all the tasks supported in LitGPT. If you want to be a bit more specific, you can do also, let's say MLU, and then it should only list the MLU related tasks. Still a lot of tasks. Let's see. Let's just use one of them. Which one should we use? Let's just do this one. Okay, so now we can use cell. It's a bit crowded there. LitGPT evaluate the model, right? Microsoft Phi2, the base model first, and tasks. Let's just use this one. And we can also define a batch size so it goes a bit faster and see how that performs. And then I can do the same thing for the fine-tuned model. This is actually the exercise. So I will leave this as an exercise for you to do the evaluation of the fine-tuned model, but let's first see what we get here. Oh, actually, it's a really bad score. Yeah, it didn't get anything correct. Let's try another one. Let's try this one. I could also just use one of the ones I tried earlier that I have here. Well, this is actually the whole MLU. Humanities, other social sciences, STEM. Yeah, this looks a bit better. So we get 28% accuracy on this task. Now as your task, try to do the same thing on the fine-tuned LLM. So maybe pause the video and see if you can evaluate the fine-tuned LLM. So how I would do it is I would just copy this and then change it with our fine-tuned one, which is out fine-tune LoRa. I will just copy this path. So this is actually a slight improvement. So our fine-tuned LLM is a bit better than the baseline LLM. And even though we only had a very, very, very small data set and only trained it for like 3 minutes, so that's actually quite nice. Okay, so this is then how we do benchmark evaluation. Of course, you can also use other tasks. You can, like I showed you before, use multiple like that, but you know, that would take a bit too much time. So let's jump into the final notebook and see how we can use another method that also evaluates the conversational performance of an LLM. Okay, so now on to the fourth and last notebook. So here we're going to use an automated way of evaluating an LLM using another LLM. So for this notebook, we assume we have a data set in the following form. So where we have an instruction, optionally the input, the correct response. So this is essentially what we had originally in the alpaca dataset. And then we added the response of the base model and the response of the fine-tuned model. So I saved it here as this file. So this was something you, as an exercise, hopefully generated in part 2. And yeah, so this is essentially containing the before and after. Before means before fine-tuning, after means after fine-tuning. I mean, what names you choose doesn't really matter. You can also call this base model and fine-tuned model. But like that, we have all these entries here. Let me go back to this one. So this is how the data set would look like. And yeah, let's first load this data set. It has 165 entries. It's only the test set, right? So we only have 165 entries. We can take a look at one of the entries. Like I said before, there's the output that we consider as correct output, and then the output by the base model and the output of the fine-tuned model. So now here's just like a utility function that we used before to format the model input. So this is just formatting the model input. Yeah, then the output would be like this, the one that is provided in the test set. And the generated model response is this one here. And essentially what we are going to do is we are going to ask a Llama 3 model to consider this input, and then given the correct output, assign a score to this response. So basically I'm saying giving the input and the correct output, score this model response on a scale from 0 to 100, where 100 is the best score, and then respond with the integer number only. So let's do this. See, I messed around with the notebook a bit, so I should first load this, of course. And then let's give it it's just JSON data. And the JSON key would be, the JSON key here is just what we call the response. In this case, let's use response before. Oops. And this would generate these model scores. Yeah, it's relatively fast, I would say. But yeah, this is also why I use small data sets here, because we don't want to wait an hour for 50,000 responses and something like that. Okay, it's finished. So let's take a look at the scores. So now we have these scores from on a scale from 0 to 100. We can actually, let's compute the accuracy. Oh, yeah. What did I do here? Oh, yeah. Oops, I made a mistake here. Wait, where am I wrong here? Oh, I see. They are already on a scale from 0 to 100. So yeah, so this should be the accuracy, right? So, or not accuracy, but a score. So we have a score now of 82 for this base model for the response before. Now for the exercise, or maybe do the same thing for the fine-tuned model, the response after that you saved as part of the exercise here in section 2. So basically how we would do this is the same way. After, and then we can append it like this. Okay, so in this case actually made the model slightly worse. Can happen. So it was probably because of the LoRa fine-tuning. Or maybe this method is also not perfect. You can try a larger model. But yeah, so we see that we got some scores that we can compare. And yeah, sometimes fine-tuning doesn't necessarily make the model better. Yeah, so in this workshop, we covered 6 topics. The introduction to LLMs, understanding how the input data is tokenized. We coded, I would say, a fraction of the architecture just to get a feeling of what an LLM looks like, how it's structured. We briefly pre-trained the LLM, loaded pre-trained weights, and then lastly, we fine-tuned the LLM. I have no idea actually how long it took. I just feel like I've been recording this video for like maybe 3 to 4 hours. I definitely need a break now. But I hope it was useful and it gave you some ideas of how LLMs work and how they are trained. So in specifically, we covered these topics, but only in brief. Each topic was maybe only 10% of what I covered in my book. So if you are interested in more information, I have a very extensive book on all of that, where, what I just covered was like maybe 10%, 20% of that. Other than that, also, LitGPT is a really useful tool in practice if you want to fine-tune LLMs for real-world tasks, because everything in the book is, I would say, more for educational purposes. It's, of course, developing a LLM that works and that can be used in practice. But here you have basically more optimized LLMs that are, larger and so forth. So yeah, if you're interested in LitGPT, here's a link to the GitHub repository. And we also at Lightning develop a platform that I used also here for teaching this video workshop. So in that sense, you can use multiple GPUs for training. And what's nice is really you can switch seamlessly between CPU and GPU. So you don't have to run the GPU the whole time. You can just switch to a CPU when you're developing code. And then once you're ready to scale it up or run it, you can then switch to GPUs. And there's also, I used Visual Studio Code, but there's also a Jupyter Lab environment. We also have a lot of examples for fine-tuning LLMs. So you can find the studio examples here, training models on 1 trillion tokens and so forth, and optimized inference and so forth. And with that, I hope this was useful. I know it was a bit messy. It was just, spontaneous, a recording I did for 3 to 4 hours now. It's not very polished, I know, but it's hopefully in some way useful to you. And thanks for listening.